Here's something you can try if you went and buy yourself a pair of sunglasses. Okay, so if you look at this one, this is a computer screen. So from the screen that you are watching our videos, do you know that your computer screen is also polarized? This light that is coming out from the screen is polarized, already plane polarized. So this means that the light is traveling in a particular direction. Notice that when the sunglasses is horizontal, I don't see any light from the screen. Can't read the text. And when the sunglasses is vertical, I can pretty much see a lot of the light. And you can see that the intensity or the brightness of the light actually changes with the angle. Right? So this rotating has something to do with the properties of polarization. All right, we're going to look at this now and also at this law called Malus Law. Hopefully I'm pronouncing his name right. I want you to look at this diagram that we have seen in the last video, where you have this electromagnetic wave here, this part that is not polarized, okay, unpolarized, and I pass it through one Polaroid where now it is plane polarized. So the light is kind of traveling in one plane, okay, vibrating in one plane, sorry. So as it travels here, it passes through another Polaroid. So think of the screen. Let's say, for example, you look at your computer screen. Your computer screen light actually looks like this already, okay, because of the property and how the screen is designed. And when I place sunglasses, so this is my sunglasses or a Polaroid, and then I tilt the sunglasses off, I want you to pay attention to the amplitude of the waves. You will notice that this amplitude is smaller than this amplitude. Okay, and then as I continue, you can see the amplitude is even smaller. So of course, we're going to reach a point where the amplitude essentially is zero, because the long chain molecule that is now vertical is blocking all the waves. You don't see anything, it's black. In Miss Ellie's demonstration video, she put two sunglasses on you. Remember, she put one on you and then she rotate the other one. This is the first sunglasses and this is the second one. Okay, so if you can find two sunglasses, very good. You can try and see. You wear one, then you make the light travel in one plane. You take the other one and then you rotate. Wow, full brightness. Wow, darkness. Wow, full brightness. Wow, darkness. Okay, this is governed by a law called the Malus Law. We're going to go to our notes now. To properly demonstrate Malus Law, we're going to draw you a diagram that looks something like this, okay? And we're going to start off with an unpolarized light, okay? And we're going to need two Polaroid, okay? So the first one, we're going to use this thing called the polarizer. Okay, this is the polarizer, okay? And I want you to pay attention to this word axis. Okay, so this is the axis of polarization. Okay, axis or axis of transmission. Meaning only light that is parallel to this axis is allowed to pass. So here is unpolarized light. And then at this point here, this is plane polarized light. Okay, this one here. All right, but one polarizer is not good enough. We need a second Polaroid called the analyzer. So these are two Polaroid, then the long chain molecule thing, the black color thing can turn. Okay, let's say I rotate the analyzer by a certain degree or a certain angle, phi. Phi? Yeah, phi. Let's call this phi. Okay, or theta. It's up to you. Okay. Now, I want you to understand here is that the electric field, what we are drawing here, this red color arrow, is actually electric field. This arrow here is to represent, because light is electric field and magnetic field, right? So this one is actually electric field strength. And you might be thinking, Miss, what is electric field strength? You hang on first. We will learn and define electric fields in A2. or later in syllabus. But you can see this as a way to represent the field or the strength or the energy of the light. It's a very, very crude way to talk about this, what to do. Okay, so this one I'm going to label this as E. Okay, the thing about electric field strength E is that it is a vector. Ladies and gentlemen, if it's a vector, we can resolve. We've done this so many times, right? Take a vector, split it into two. Okay, so right now, what I have here is actually E. You see this one up here? This one up here is E. And if I tilt the Polaroid at an angle phi, this means that the axis of the Polaroid, right, this one is the axis of, the axis is not this direction. Previously, it was this direction. So when it passes through the first polarizer, only the vertical one remains. Okay, now when it passes through the analyzer, only the part of the vertical that is along the axis of the analyzer will pass through. So by vector resolution, okay, you know this, it's gonna label here, this will be E cos phi. This one is allowed to pass the analyzer Polaroid. Okay. Teacher, what about the other one? This one here. This one how? This E sin phi. This one is absorbed. Okay. So GG. This E sin phi is absorbed. So it doesn't pass. Okay. It will attenuate. Basically, it will lose energy. Maybe the Polaroid will get a bit hot if it's like a very intense sunlight. I don't know. But generally speaking, the energy is absorbed. So only this one is allowed to pass. Okay, so I'm going to label everything for you. We know, or last time in the previous video, you understand that every wave has energy, and we like to represent the intensity as a way to talk about the energy of the wave. So let's say this is intensity I0. Okay, this wave here, the unpolarized light. Okay, and here your intensity is, let's say, I1. And I1 happens to be I0 over 2. Half of it is filtered over. Okay? And then, why is half? This one, you can click on the link, okay, that's below. But basically, the whole idea is we want the average of this light. Okay? And the average is half. Okay? Half of it is filtered away. This one needs a lot of statistics and also integration. So it's a bit out of the syllabus. Okay, but what we know is that we put on the sunglasses, the sun is less glaring, right? So the energy drops by half. Okay, and then here, let's say I call this I2. Okay, so basically the polarized wave of intensity I1 will be reduced in intensity when it is incident on the analyzer, right? But there's a second thing here. Let's say this electric field here is E0. Oh, okay. So then, once we resolve and we take the parallel component, this will be E0 cos phi. So not. Okay. So this is the component that is parallel to the axis, the one that is allowed to pass. It's a vector. We can resolve. Can resolve the electric field as a vector and take the one that is parallel to the axis of the analyzer. So this electric field and magnetic field random combo pass through the first polarizer so that we know that it is on one plane. This is why the first one is very important. Without the first one, right, you can't really see anything when you rotate properly. Okay, the reason why you could see it in the reflected dashboard, if you remember the one from the previous video, is because the reflected wave is already plane polarized. So you put your sunglasses, you can see the receipt of the dashboard will begin to, the reflection will not be there anymore. But If it's not reflected, if it's just light entering the Polaroid like this, then I need to first put a polarizer so that I get this E naught, clean E naught. Okay, and then when it passes through, it will be E naught cos phi. The angle is the angle between the wave and the axis of the analyzer. Okay, so let's write all of this down. Okay, number one, I'm going to say that to remind ourselves that number one, intensity I is proportional to amplitude square. Remember this from previous lecture? So I is proportional to A squared, okay? But also, the amplitude of the wave is actually proportional to the electric field strength. Because we draw the electric field like a wave, right? So the peak of the electric field is the peak of the wave. It's proportional, like it's not the same, but it's proportional, okay? So because of this, I can then say the intensity is proportional to the electric field strength square. Ooh. Okay. So then I can say I1 over I2. Okay, what is the electric field of I1? I1 is E naught. So I'm going to put E naught here. And what is I2? I2 is this one, related to E naught cos phi. So I'm going to put here E naught cos phi. Don't forget, got square, got square. Don't forget the square. Don't forget the square. Okay, then teacher, then how? Then we can simplify and cancel the E naught, right? And I guess, you can run it in different ways, but I will label them for you. I naught, don't forget the square, cos square. Okay, I will label this for you. Or alternatively, I can write this one as I is equal to I naught cos square theta. They are the same thing. So please understand that in physics, hopefully by now you will know that this thing is just a symbol to represent something. It is not always consistent. But the idea here is you are sending a light into the analyzer. So for this I, this one is intensity of polarized wave incident on analyzer. Okay, that is what I1 or I is. This one here. After I pass through the unpolarized light. Okay, what about this I2 and I or I naught? This I2 or I naught will be intensity of polarized, actually intensity of wave is also polarized, but anyway, wave after passing the analyzer. And what is theta? Well, my friend, theta or phi, this two is the angle between the plane polarized wave and the axis of the polarizer. Sorry, axis of analyzer. This is Malus Law using this equation. Okay, so you need to remember the relationship, okay, which has a cos square, right? The square here comes from the fact that I is proportional to A square. And because of this, I is proportional to E square. Okay, so that's why there's a cos square angle here. So in a nutshell, right, what I'm trying to say is your intensity I that enters the analyzer is equal to I that exits the analyzer cos this angle, the angle of rotation. Understand that this angle is the angle between E and the axis of your analyzer. All right, the part that is allowed to pass. If you understand this, then when you look at a diagram like this, it kind of sort of makes sense. When it is tilted at an angle, only those that are parallel to this angle is allowed to pass. Okay. Here is a handy dandy 3D simulation. So remember, we already polarized using the first Polaroid, and then whatever that comes out of this first square is plane polarized. This wave here is I0, okay, or I, whichever works, all right? And you notice that this angle is 0. I'm not sure if you can see. Zoom in a bit, 0, okay? So you can see that the amplitude is maintained the same, okay? So I guess if you want to, I can rotate it a bit so you can see that, you know, it's the same plane, okay? So when you think about polarization, right, please understand that when I rotate the Polaroid, what I'm rotating is also the direction of the wave that comes out. Okay, this is the direction of the wave that comes out. Okay, and as you travel, you can see the amplitude of the wave is dropping. Because anything that is not parallel to this red color line, which is the axis, this parallel lines is the molecule chain, the long chain molecule. Okay, but what we care about is the axis of transmission, which is this red line. So if let's say I make the axis just nice, like that, 90 degrees. Come on. Okay, so at 90 or 89, sorry. Okay, there's like no wave passing through, like almost none. Okay, so when this axis, when this long chain, this parallel black color line is parallel to the plane polarized wave, everything gets blocked, cannot pass through. So the plane polarized electromagnetic wave gets blocked. If I want it to pass through, I have to rotate it more. And you can see the intensity will increase to maximum. So it goes from maximum, decrease, minimum. So how much did I rotate? Okay, I want you to look at this blue dot. I start with here, right? This one is maximum transmission. Okay, and then it decrease until 90 degrees. This is minimum. So be mindful about that, because I'm going to sketch a graph later to represent the intensity of the wave that passes through this analyzer. This gray one is the analyzer. Okay, so let me continue rotating first. I want to turn 360 degrees. Okay, so as I rotate some more, you can see I get more waves coming through. Again, observe this wave. It is always parallel to the red color axis of transmission. Okay, still following Malus Law of I is equal to I square cos angle. Okay, so I'm going to continue rotation. It will increase to maximum. Okay, and then decrease to 0. And where did we start? Remember, we started here. And then increase to maximum. So basically, we have 2 points where we have 0 transmission. Here, 90 degrees, and here, 3.5 quarters, 270 degrees. All right, so I'm going to sketch that now. Okay, before we sketch, we have to be very careful about the reference angle. Okay, so right now, I want you to imagine, right, what happens when phi is 0. Okay, when phi is 0, this axis of transmission is parallel to E0. So you get the maximum goodness. Okay, so you can obviously substitute here. Okay, you can press your calculator. Okay, I want to remind you this is cos square. Okay, so you press your calculator, cos 0 is 1. 1 square is 1. So which means here you will get the peak. Okay, so maybe this one will be I1. Okay, so this one is the graph of I2 against the angle phi. Based on the drawing on top, okay? Based on the drawing on top. So we're going to start off here where this is 0 degree. And then somewhere here, you will get 90 degree. Now what happens when it's 90 degree? You imagine this axis, huh? I will rotate, and now this axis is parallel, or rather horizontal. So it's kind of like 90 degree to E0, right? If it's 90 degree to the E0, to this thing, to the plane polarized wave, will you get any wave? No, you won't. Okay, remember this one? So when, look at the red color line, when the red color line is 90 degree, I don't get anything. Nothing. Okay, so in this case, if we are going to go back to this one, this intensity is maximum, and as it decrease, 90 degree, minimum. Okay, so I'm gonna just draw a few points. Here. And then when we rotate 180 degree, and this rotation is another 180 degree, is going to be, so it went from this to this, okay? And then after that, another 180 degree, we will get back this one, okay? So let's say this is the upward direction, you rotate to this direction, then you rotate to this direction. This one is still parallel, so you will get back the maximum value. So I'm going to go back to my graph. I'm going to find 180 degree. This is just a rough sketch, okay? And then this one, go back to I0, or the maximum amplitude. Okay? And the cycle kind of repeats itself. So in the end, you will get a graph that looks like this. I mean, it is a cos square graph, so you can plug into GeoGebra and see, but it is still very sinusoidal. Okay, so go down. I'm going to try my best, okay? And then come up. Like that. Okay, so of course we're going to repeat again. So what I'm going to do is I'm going to do this step you can't do, which is to copy and paste. We're going to repeat the cycle. If let's say it rotates for 360 degrees. Wow, teacher, you cheat a bit. A bit lah. So the maximum will be there because 0 is equivalent to 360. So those of you who are actually doing a bit more maths than normal, maybe you are doing further maths, or maybe you're just doing normal maths, okay? If you know how this graph look like, the function of this graph is I2 is equal to I1 cos phi. This angle, this equation. Okay, so this is a cos square. Because of the square, right, you actually peak 2 times. All right, so I'm not really going to go in depth about how this graph look like, but as a short nutshell, if let's say you struggle with sketching graphs, the cos graph will look like this. This is cos theta, and this is theta. This is my cos graph. Okay, this is very important, even if you don't do maths, okay? For A levels, some basic maths like this is needed for physics, okay? So if this is cos square theta, I'm going to square the blue graph. Now you chill first. When I want to square something, I won't get no negative numbers, bro, because I square it. So if I square this thing, I'm only going to have positive graphs. I'm going to just make more space for myself. Theta, okay? And let's say this is the vanilla cos theta graph. So this is 1, negative 1. Okay? So what happens when you square 1? Teacher, 1 square is 1. So smart like you. See? Yeah. This is 1. What happens when you square 0? Oh, teacher, 0 square is 0. 0 square is 0. 1 square is 1. Yes, look at you. So good in maths. Okay. What about negative 1 though? Negative 1 times negative 1 is 1. Negative is positive. So you're going to get this one again. Oh, interesting. So this is the graph that I'll get. This. I'm going to try my best to draw it, okay? Without sheets. You see, you see it's the same, same shape. Okay, so I'm not going to really talk too much about the curvature. It's not the same shape, but you can sort of like look at it this way. All right, so the cos-square graph will look like this. We'll be sketching a lot of cos-square graph a bit later, especially in your A2 syllabus, cos-square, sine-square. But in a nutshell, what we have now is the peak, the 0 point will happen twice when you rotate in a 360 cycle. Very important when you do past year question, as we work through the examples, is to be very sure which angle they're talking about and where they start rotating. Later, just to annoy you, right, they start measuring the angle from here. Hiya, yeah lor. Later, to annoy you, right, they change the vertical axis of the Polaroid and make it horizontal. Hiya. You are smarter than that. So always remember, we take the one that is parallel to the axis of transmission and we filter out the rest. Okay? And to find the intensity of the one that passes through the Polaroid, we can use Malus Law, which is I is equal to I naught cos square theta. Okay? So this one, this angle here is the part that passes through parallel to the axis. So that's why it's the angle between the plane polarized wave and the axis of the polarizer. And why is this polarizing thing so exciting? Well, I'm just going to briefly mention this because the video is getting a bit long. Uses of polarizing, as you can tell, mainly is for glare reduction in sunglasses. So you wear sunglasses when you drive, like Miss Ellie, and you will notice that, oh, I cannot see the dashboard, some random tree reflect, I cannot see. Perfect vision of the road in front. Very good. Okay. Sometimes, right, when you watch 3D movies and then they give you that kind of glasses, or you know, I'm a bit boomer. During my generation, right, they will put their 3D glasses like in a magazine or got cardboard one, then can cut out and fold and make glasses. Wow, I feel like so pro. Okay, so this polarizing is actually looking at light that is traveling in random direction and making it travel in the direction that you want. And then after that, tilting a little bit so that you get that effect. Okay, so this one can use to isolate two images to find your 3D cinema. All right, and also generally we tend to use this for stress analysis as well. Maybe we pass through light through a certain structure and observe the polarization of that light through a Polaroid. Because if we can understand how light reflects on the structure, we understand how the structure is being made. But all this is not really in your syllabus. I just want to show you the exciting stuff about polarization. Okay, so what do you need to know? You need to know the difference between unpolarized, plane polarized, and what happens when a plane polarized passes through an analyzer. You need to understand that the component that passes through the analyzer is parallel to the axis. Okay, so if I pass through the first polarizer, my intensity dropped by half because of laws of average. And then after that, the intensity will continue to drop. Drop by how much? We will consult Malus Law. I is equal to I naught cos square theta. Polarizing is quite fun, and also to think about electromagnetic wave in such random propagation is a bit brain-breaking. So take a chill pill and meditate on this beautiful light that is coming towards you. And I'll see you in the example videos. Bye-bye.